Hi, today we're going to be talking about the sandwich theorem or the squeeze theorem. So as I'm talking, go ahead and title your notes, sandwich theorem or squeeze theorem. And what this theorem really aims to do is use more familiar functions to help us draw a conclusion about a problem that might, when we try our normal methods of analyzing limits, we just can't figure out what the value of this limit is. So then we use more familiar functions to help us draw a conclusion about it. So let's, its namesake is sandwich theorem. And so what I'm going to do is draw a bologna sandwich. So when you think about putting together a sandwich, you need the two pieces of bread, then you need the bologna in between. So what we have on, that kind of looks like a hot dog, but that's okay. So the way I'm going to describe it is we have the top bread, we have the bologna, then we have the bottom bread. And so if I were to write three functions, let's say we're given three functions and we know that the bottom function is g of x, it's less than or equal to the middle function, which is f of x, which is then less than or equal to h of x. And this is provided to us. We know that this is true. And so in our picture, we're going to say that g of x is our bottom bread, the bologna is f of x, and h of x is our top bread. And so we'll say that it's also provided that this inequality is true for all x not equal to c in some interval about c. And so I'll describe what that means. So in a picture, a graphical picture of our functions, let's go ahead and draw. You have three different colors out. Your top function is going to be the top bread, which we called h of x. So in that initial color, can you go ahead and draw a function that looks like that? Okay, and we'll call this point right here, where it kind of dips down, we'll call that point C. Okay, and now let's switch colors, and we're going to draw the bottom bread. And the bottom bread is going to meet at point C, where it's equal to. And I forgot to label, so this is our bottom bread. This is g of x, and our top bread was h of x. And then we have our bologna in between. So in a different color, let's draw our bologna being f of x. And so how are we going to use this, apply this using sandwich theorem to make a conclusion about the functions that we have here? So we haven't talked at all about limits. I'm going to also add one more thing to our picture here and call the y value for C, L. And I'll do a different color so you can see here. But this y value right here, where it meets is L. All right, so we have our inequality, and let's say that we knew another piece of information, another key piece of information, and that is that the limit as x approaches c of your bottom function, g of x, also happens to be equal to the limit as x approaches c of your top function, h of x, and that value is L. Okay, so if, let's put the word if this is true, so if the limit of those two functions are at c is equal to L, what conclusion can we draw about the bologna or the middle function? Then, if you guessed it, our conclusion being that the limit as x approaches c of your middle function, well, that also has to be equal to L. What happens is if you think of it as a sandwich where you have your f of x is squeezed in between, the bologna is squeezed in between the bread, it must therefore behave the same way as your top and your bottom function as it approaches c if both the limits of the top and the bottom function happens to be equal to that same value. So physically, you can see that must be true. So let's go ahead and apply it in a limit math problem. So we have example number 1, we're asked to find, so it'll look like any old regular limit problem, limit as x approaches 0 of an unfamiliar function, x times sine of 1 over x. And that's it. That's our problem. So we try, let's say we see this and we try what we always try, which is direct substitution. We plug 0 in, we get, well, this one is easy. We have two functions, we have 0. But when we plug 0 into x, we get 1 over 0 or something that's undefined. Then we can't evaluate that any further. So is there another way to think about this problem? Now I want you to think back to pre-calc honors and to algebra 2 trig and think about the amplitude of this part of the function, just the trig function alone. Okay, so we're going to try to break this down to more familiar functions by first analyzing and taking that sine function. So think of sine of anything, sine of 2x, sine of 5x, sine of 6x. We learned from last year that those sine functions, because they don't have anything in front of it, has an amplitude of 1. And having an amplitude of 1 simply means that our highest value is 1 that sine function can achieve, and the lowest value it can achieve is -1. So it oscillates between -1 and 1. So from there, let's say this is a compound inequality. So now what I'm trying to do is take what is familiar and then build it so that it gets closer and closer to the actual problem that I want to analyze. And so I noticed that the sine of 1 over x isn't the actual function we're trying to analyze, but x times sine of 1 over x. So what we'll do from there is times the entire compound inequality by x. If we distribute and times each one of those components by x, we get negative x is less than or equal to x times sine of 1 over x. And aha, I noticed that my middle now has the function that I'm trying to analyze. And so if I evaluate the limit as x approaches 0 now of each one of the components, I end up with the problem that I'm trying to solve for, being the middle component of this compound inequality. And so the question is, well, can I analyze these more simple functions, the upper bred and the bottom bred? And yes, those are really easy to do using direct substitution. Using direct substitution, I get 0 plugged into negative x is 0. This is my initial problem. So I'm just saying, let's copy that down here. And then plugging direct substitution 0 into the limit on the right, we get 0 as well. So our conclusion, therefore, is that the limit, this problem that I began with, is got to have a limit that is the same as the top and the bottom function at that point x equals 0. That 0 is where our c value is, and you'll notice that, again, it must be true that you have that point being the same common limit. If the top and the bottom is the same, our middle has to be the same. So our conclusion is that the limit must be equal to 0.